This is a blockchain demo. We're going to do this in a very visual way, though. I'm going to make it very easy to understand by stepping through the key pieces of what a blockchain is in a visual way. But before we get started, we need to take a look at this thing that we call a SHA-256 hash. Okay, and a hash, this is one of them right here. A hash looks like a bunch of random numbers. And essentially what it is, it's a fingerprint of some digital data. And it just so happens it's the fingerprint of whatever I type in this box. So if I type my name, Anders, into this box, you see that the hash has changed. As a matter of fact, it changed every time I typed a letter, right? So I'm going to go back to, so it says Anders. Okay, so this is the hash of the name Anders, all lowercase. It starts with 19EA, right? Okay, so if I delete that and I go again, type Anders again, you can see it starts with 19EA, the same exact hash. In that sense, it's a digital fingerprint of this data. Whatever data is here, every time you type exactly the same data, you get exactly the same hash. And I can type anything I want. So you can have nothing, like this, E3B0, that's the hash of nothing. Or you could type tons and tons of stuff. As a matter of fact, you could put like the Library of Congress in here and you would get a hash. And the interesting thing about it is, regardless of if there's a tiny amount of information, no information, or the entire Library of Congress, you're always going to get a hash that is this long, this many characters. You're not going to be able to pre-guess what this is. You kind of have to put the Library of Congress in here to figure out what the hash is, but you'll always get exactly the same hash regardless of how many times you put exactly the same information in. So what I'm going to do is extend this idea of a hash into something that we're going to call a block. All right, so let's take a look at a block. So this is a block, and it's exactly like the hash. It's just that data section I've broken out now into 3 sections. One called block. This is just some kind of a number. This is block number 1. A nonce, which is just yet another number. We'll go into what that is in a second. And then just some more data, just very similarly to the way that we had it before. However, the hash of this, which includes all of this information up here, is down here, and it begins with 4 zeros. You see that? Okay, that's a relatively unusual hash. Most of them are not really going to start with 4 zeros like that, but this one happens to. And because it does, totally arbitrarily, I'm going to say that this block is signed. Okay? So what would happen if I were to change any one piece of this information? Let's say if I were to type something here, right? The hash is going to change. And what's the chance of, if I type letters, this hash is going to start with 4 zeros? Pretty low. It's probably not, right? So let's see what happens when I do that. I'm just going to say, hi. Oh, look at that, right? This hash does not start with 4 zeros. And so the big background here has turned red. So now you know that this block with this information in it is not a valid or a signed block. Okay, and that's where this nonce comes in. This nonce is just a number that you can set to try to find a number that fits so that this hash starts with 4 zeros again. All right, so how do we do that? Well, let's start with 1. Does that start with, no, it's 3, 2, 7, that's not 1. So let's try 2, FF now, 3, 4, 5, 6. You get the idea. Like I could sit here, there's one that starts with a 0. I could sit here all day typing these numbers and trying to figure out one that actually is going to hash out to something that starts with 4 zeros. Going to take a long time. So here I have my little mine button. I'm sure you've been wondering what happens if I press that. So what's going to happen when I press this mine button is it's going to run through all the numbers from 1 all the way up to try to find one where the hash starts with 4 zeros. And this process is called mining. Let's do it right now. So now it's checking all of the numbers from 1 all the way up. Whoop, there. Now it's stopped at 59,396. And that one just happens to hash out to something that starts with 4 zeros. And it satisfies my little definition of what a signed block is. Okay, so that's a block. Now, can you tell me what a blockchain is? It's probably just a chain of these blocks. Well, how do you put them together? Let's do that. All right, so here's my blockchain. I've block number 1. It has some kind of a nonce just like before. There's some data area to it, but then it has this previous. And here it's a bunch of zeros. Let's roll forward. So this is block 2 and block 3 and 4. This blockchain has 5 blocks on it, right? The previous here starts with 00 AE8, right? Is this number, AE8. And then this previous, B90 is this one over here, B90. So you can see that each block points backwards to the one before it. And you remember that the first block over here, there actually is no previous, so it's just a bunch of zeros. It's actually just a fake number. Okay, so just like we did before, what happens if I change some information here? Right? It's going to change the hash of this block and it's going to invalidate it, right? Well, let's try that. So I'm going to type hi again. Sure enough, that block is invalid. All right, just as we assumed. But what would happen? I'm going to fix that now. We'll go back to something that worked. What would happen if I change something in this block? Right? It's going to change this hash, but this hash gets copied up to this previous. So it's gonna change this one too, right? So it should break both blocks. So let me try typing hi in there. Sure enough, all right? So we can go back as far as we want, to some point in the past and break that block, and it'll break all the blocks since then. Everything before is still green, but this one is red. So if I wanted to, change something in this blockchain, I could just go over to block number 5 right here. We could change it. I'll put hi, and then we could remine it, and pick a different nonce. We'll do that right now, and we could essentially alter the chain. So we've done it, so that we should be good now, right? All right, well, what happens if I go back in time to here and I break it here? Now I have to mine this block, which will pick a nonce that makes this block hash out to 4 zeros, if we can find one. Sometimes it takes a while because it's got to run through a lot of them. There it is. It found one at 138,000. All right, but this one is still broken because although this one starts with 4 zeros, adding the 4 zeros with different stuff up here still makes this block hash out incorrectly. So I also have to mine this block. All right. And that takes some amount of time. That one was a little bit quicker. And then I have to mine this block to fix it. All right. So what we're showing here is that if I go and change this last block, all I have to do is remine this block. If I go way back in time to back here and I make a change like that, I'm going to have to mine this one, this one, this one, and this one. So the more blocks that go by, the more blocks in the past that we are, the harder and harder and harder it is to make a change. And so that's how a blockchain is going to resist mutation, resist change. Okay, so now, I did. If I do this in this block here, you can see that I've changed it to hi and I remined it, blah blah blah. How would I know that my blockchain has been remined? All right, let's take a look at that. I'm going to hit this little distributed thing. So now we have a distributed blockchain. It looks exactly like the last blockchain, okay, up to 5. But this is peer A, the first peer. If we go down here, you can see here's peer B, and it happens to have an exact copy of the blockchain. There's actually also a peer C down here, right? And this could go on forever. There's many, many peers out on the internet, and they all have a complete copy of the blockchain. So in this case, if I look at this hash, it's 00E4B, all right? If I go down to this one, I notice it also has E4B. If I go down to this last one, it has E4B, so they must be identical. And I'm going to demonstrate that by going here and typing something. I'll type hi again, and then I will remine this block. And I've got some other number, and now it's put some other number up here. So I should be able to mine this block. Okay, now all the chains are green, right? They're all green. However, this chain says the last hash is E4B. The bottom one says that too, E4B. And this middle one here says 4CAE. So I know just by glancing at this one little hash that something is wrong in this blockchain, even though all of the hashes start with 4 zeros. I know that this one is different. And it's different because I have two. It's essentially 2 against 1. We're a little democracy here, right? This guy argues that it's E4B. This guy argues that it's 4CE, it's 4CA, and this one is E4B. So E4B wins. So that's how a completely distributed copy, having a copy on many different computers, they can all very quickly see if all of the blocks are identical. And remember, blockchains can have, 400,000 or 500,000 blocks very easily. So rather than checking through all of them, all you really have to do is look at the hash of the most recent one, and you can see that if anything in the past, anything way back here was altered, you can tell by looking at this at the last block in this in the chain. It's going to hash out to something that doesn't start with 4 zeros and looks very different from what the hashes on the good chains are. Okay, so that's a blockchain. That's the entire thing. There is no more to it than that. But it's kind of not really useful because we don't have something in this data area that means anything. I keep typing my name or hi, and that's sort of irrelevant information. So what we really want is a token. So let's do a token on our blockchain. All right, now look at this. So I have this token just totally arbitrarily. I'm calling these, I guess, dollars, right? So we have $25 from Darcy to Bingley. $4.27 go from Elizabeth to Jane. You get the idea. It's basically there's all these transactions that are happening. And I've just replaced the data with these transactions. And just like we saw before, so there's multiple blocks here. This one has more transactions. It doesn't matter how many transactions there are. There can be many or there can be few or none. If we keep going forward in here, just like we saw before, if we go down, we notice we have all these other copies of the same blockchain, right? So now here's where the immutability is important. If I change something back here, you'll notice that this is, A7FC, blah, blah, blah. It's something else. So it's something different than what's down here. So in this way, it's very important that if I were to go back in time and change some value that we would notice. It's very important with money that you don't lose track, and that's the whole point of using a blockchain here. This is the whole point of resisting any kind of modifications, of things that have happened in the past. So that's the reasoning behind using a blockchain to remember tokens. Now, one thing I would mention here is that we're not listing, Darcy has $100 and he's giving 25 of it to Bingley. The only thing we're saying is Darcy gives 25 to Bingley. We're not remembering a bank account balance. We're only remembering money movements. So this begs the question, does Darcy have $25? Well, we have a problem here in this version of the blockchain. We don't actually know if Darcy has $25. So let's look at a Coinbase transaction. So if we look back here, a Coinbase, we're going to add a Coinbase transaction to our blocks. And this is very similar to what we've seen before, but we're just adding a Coinbase at the top. And what that's saying is we're going to invent $100 out of thin air and give it to Anders. Okay, there's no transactions in this block because nobody had any money previous to this. In the next block, another $100 comes out of nowhere and goes to unders. I'm a fan. I love it, right? I'll take $100. Now we have some transactions. You can see that they're all from unders. They're all from me because I'm the only one who has any money at this point. So I'm sending 10 of my dollars to Sophie. Do I have $10? Yeah, I do. I look back and I see that this Coinbase transaction has given me 100, so I have at least 10 and I can send it on. And you add all these up and they don't go over 100, and it follows sort of a basic rule of a currency. Like, you can't invent it out of thin air. You can't create money out of thin air. Its dispersion is controlled. So now if we look at this blockchain that we've created and we zip forward in time and we notice that we see that Jackson is giving Alexa $2. And so does Jackson actually have $2 to give Alexa? Well, we go back a block before and we see that Emily, who had gotten $10 from Anders, gave 10 to Jackson. And so Jackson does have the money. So we can just go backwards and find that out. And that's actually one of the benefits of having a previous here. It's easy to go backwards. We just look for the block that looks like that has that hash. And here it is right here, right? So it points to blocks back in time and allows us to trace the provenance of any coin that we want. So that's a basic blockchain, and we're running a currency on top of it. And as you know, blockchains there are many copies. Everybody has a copy of it. So if we mutate this and make it $6, these go invalid. It does not agree with these blockchains down here, these copies of the same blockchain down here. So this resist tampering, which is what you want for a currency, it works very well for things that are small and transactional like this. I'll go ahead and fix that. And they're just a very efficient way to handle agreement on what has happened in the past. It's kind of this immutable history that goes down with time. So that's a basic blockchain and a token on it. We're glossing over some main points, but if you dig into the demo and click through these things and play around with it, you get a better and better idea of how this works. There will be a part 2 where we go into a little bit more detail about how the transactions are created. Till then.